Hello friends, welcome back to this video on analog communication. In this video, we are going to see the properties of the Bessel function which we have already introduced in my previous video. So in my previous video, I was talking about the wideband FM. So in my wideband FM, the modulated signal was represented as AC summation n is equal to minus infinity to infinity j n beta cos omega c plus n omega mt. So this is my Bessel function. I introduced the frequency spectrum of the modulated signal as well. The frequency spectrum was looking like this. So I introduced one of the properties to discuss the frequency spectrum in my previous video as well. So here we'll see in detail what are all the properties of the Bessel function. So as you can see from the chart, the Bessel function's value depend upon the value of n and the value of beta. So first we have to see what is the beta. So let's suppose from the chart you can see if the beta is 0 and n is 0, the value of j, the Bessel function, would be 1. You can see it from the graph. Now you can deduce the conclusion if you see all the values from the chart that the 0th value, the j0 beta, you can see from the graph that when n is 0, I can see all the values in that column and I can deduce that it contains the significant portion of the amplitude. So it is the largest number. After that, the value continuously decrease. So if I see all the values, I can deduce one more conclusion that all the values are real for every value of n and for every value of beta. So nowhere in the chart you can see any imaginary number. So j and beta is always real for all n and beta. So when I was drawing this frequency spectrum representation, for that what I can do, I had to plot this in frequency domain. So what I did, I took the frequency spectrum of cos omega c plus n omega mt, because this is a real number, it's a number, it's also constant, AC is constant. So now frequency spectrum will depend upon cos, and the frequency spectrum of cos was AC by 2 del omega plus omega c plus del omega minus omega c. So this is the frequency spectrum representation of cos omega. So now I plotted the values of the del functions here, but here it is multiplied by different Bessel function. So here it was multiplied with j1 beta, so n was 1 here, but here it was multiplied by j minus 1 beta. So to find out the value of the Bessel function at the negative portion of n, so this formula is used. So the negative value of n into minus 1 raised to power n is equal to positive value of n's Bessel function. So the j and beta represents the value of the Bessel function at positive n. This represents the value of the Bessel function at negative n. So when I multiply it with minus 1 raised to power n, I'll get the j and beta. So it's the relation between this positive and the negative part. So I can deduce the relation for even n and odd n. So when I say n is even, so this minus 1 raised to power even would be 1. So now j n beta would be equal to j minus n beta. So if I need to find out j minus n beta, it would be directly equal to j n beta. Now for odd n, so here n is odd. So for n is equal to odd, I'll put this power to be odd. So when the power is odd, this minus 1 will be minus 1. To the power odd would be minus 1 outcome. So j and beta would be minus of j minus n beta, or I can write j minus n beta is equal to minus of j n beta. So this is the reason why I plotted the j1 beta in the upside and j j minus 1 beta in the downside. So it is equal to minus of j1 beta. So now I can see from the graph how I can plot the values of different values of j for different n and different beta. So I can find out for different minus n as well. So now coming to the next property. So if I am considering my modulation index to be small, so then only these properties would be applicable. So when the modulation index is small, so beta is small, so now that time j and beta, the Bessel function can be represented as b by 2 raised to power n upon n factorial. So now from here we can deduce various values of j. So now if I consider the value of beta to be very small, so from the graph you can see when the value of beta is 0, j naught of 0 is 0, j naught of 0 is 1. You can see from the graph. Now j naught of 1, you can see it is also nearly equal to 1. So j naught of beta, for the small values of beta, it is nearly equal to 1. You can see it directly from the graph. So now coming to the next property, j1 beta is nearly equal to beta by 2. So now put the value of 0 here. When I put the value of 0, so now beta was 0. So when it is 0 raised to power n, I'll represent it as 1, and n factorial, 0 factorial is 1. So j naught 0 is 1. Now I'll put the value j1. So n is 1 here. So 0 raised to power beta by 2 raised to power 0 was 1. Similarly, if I put 1, so it is beta by 2 raised to power 1 upon n factorial. 1 factorial would be 1. So it is beta by 2. So now similarly if I put large n, so at the large n this n factorial would be very large, and beta, because beta is very small, beta is small, so beta by 2 would be small, and if I took the nth power of a small value, it would be a small number, and if it is divided by n factorial, I'll get 0. So from the graph also you can see, if I increase the value of beta, then only, or the modulation index, then only I'll get the side bands. So from here you can see, if I have 0 beta and 0 n, so that time I have only one side band. So here I don't have any upper side band and lower side band. So this is just one signal which is represented. After that I have two signals. For the one signal I have the lower side band as well. So now you can see, if I am increasing beta, then only my side bands would increase. So now from here we can deduce a conclusion that the bandwidth would depend upon the modulation index. In the narrow band frequency modulation, what I said, that if the modulation index is less, then only it is narrow band FM. So from here also you can see that if beta is less, then we don't have many side bands, and obviously because we don't have side bands, the bandwidth spectrum would be less. So now I hope you are very clear up to this term. So now this property would be used when we will discuss the power of the wideband frequency modulated signals. So this property is that, so summation n is equal to minus infinity to infinity, Bessel function square is equal to 1. So now the beta is same and I am changing the value of n. So now you can see from the row, if I take the every element of the row and I square the element, if I add them, now take any row, add the square of the every element, you will get 1. So we'll use this property in the power calculation as well. So now we deduce these conclusions that for small beta only j naught and j1 beta are significant. You can see it from the chart, and I have already explained it in the narrow band FM as well, that if I have less beta, the modulation index is less, the information is contained in the upper sideband only. So I have one sideband only here. So now the next conclusion is that in the spectrum the amplitude contains the information. So here you can see the amplitude is J0 beta. Here it's the function of J1 beta, J2 beta. So the Bessel function is containing the information. So from here we can deduce the conclusion in the spectrum. So here we are talking about the spectrum. If I talk about the time domain, so in the time domain the frequency is containing the information, but in the spectrum the amplitude is containing the information. So here I'll conclude my session on the properties of Bessel function. I hope you are clear with the properties of Bessel function. If you still have any doubt, you can put the doubt in the comment and I'll try to resolve it as soon as possible. I hope you like this video. If you like it, share it with your friends, subscribe the channel and push the like button. Thank you.